Okay. Now, beta, first of all, why are we discussing the spherical trigonometry? Spherical trigonometry is required because we have understood the PZX triangle, we have understood the rational horizon diagram. Now, to solve any questions of celestial navigation, we need to know the method how they can be solved. Now, this PZX triangle which we have is made on the surface of a sphere. We have the celestial sphere, so it is made on the celestial sphere. And if we want to solve it, we should know the formula which are used in these triangles, that is spherical triangles. So that is what we are going to see in this spherical trigonometry presentation. We will see what is a spherical triangle, what is a great circle, what is a small circle, and we will see two important formula. One is the cosine formula and the second one is the Napier rule. So this is what we are going to see. So let's get started.
So first we go into the concept of a great circle and a small circle. We have the diagram on the screen now. Now this is the diagram of a sphere. You can consider this sphere as the earth. The points at the top and bottom represent the 2 poles. You can see the North Pole where the pointer is right now. And the bottommost point you can see the South Pole. And exactly midway between them, this dotted line which you see is the equator. Now on a sphere or on the surface of Earth, a great circle is a circle on a sphere or on the surface of Earth whose plane passes through the center of the sphere. The great circle has the same diameter as the diameter of the sphere itself. The purple color circle which we see in the diagram is a great circle. So you see this purple color circle which we have in the diagram is a great circle because its plane, the plane of this purple circle, passes through the center of the sphere. The center of the sphere is represented by point C. So we can see that the plane of this circle passes through the center of the sphere. So this is a great circle. Now you can see the diameter or the radius of this great circle is going to be the same as the diameter and radius of the sphere. They will be exactly the same. Now why is it called a great circle? Because this is the biggest diameter circle which we can draw or have on the surface of that particular sphere. It is not possible to draw a circle having a diameter greater than this that should lie on the sphere. So that is why it is called as a great circle. Now, as we have seen, the center of a great circle matches with the center of the sphere. To give you an example of a great circle, we have the equator on the surface of Earth. You can see the equator as a dotted line represented here in the diagram. So equator is a great circle. The plane of the equator passes through the center of the Earth, as well as the center of the equator is the same as the center of Earth. It is the biggest diameter circle which we can draw on the surface of Earth. So equator is a great circle. Also, like equator, all the meridians running from North Pole to the South Pole, all the meridians are great circles, or you can say parts of great circle. Now, a meridian and its anti-meridian or inferior meridian combined together forms a complete great circle. Like say, for example, if you consider the Greenwich meridian and the 180-degree meridian, if you join them together, it forms a complete great circle on the surface of the Earth. Now, we can only draw one and only one great circle passing from any 2 points on the surface of Earth. If you have two particular positions, two particular points on the surface of a sphere or Earth, there is only one and one great circle which passes through them. Now, there is one exception to this principle, this statement, this fundamental, and that is if these points are diametrically opposite. If these points are diametrically opposite, then we can have an infinite number of great circles passing through them. Like you have in the case of poles. The poles are diametrically opposite, so there can be infinite number of great circles that can pass. As an example, all the meridians 0 to 180 degree east and west are all great circles, and they are all passing from these 2 points, that is the North Pole and the South Pole. So 2 points which are diametrically opposite, infinite number of great circles can pass through them. And if we have 2 points or 2 positions which are not diametrically opposite, there will be one and only one great circle which will pass from both those points. Now, moving on to the concept of a small circle. A small circle is a circle on the surface of a sphere whose plane does not pass from the center of the sphere. Like, say, for example, the blue color circle which we see in the diagram, this one, this is a small circle, because you can see the plane of this particular circle does not pass from the center of the sphere, which is at point C. So all these circles whose plane does not pass from the center of the sphere are called as small circles. The diameter or the radius of the small circle will be less than the diameter of the sphere. And the center of a small circle is not the center of the sphere. We know their centers are not matching. The centers of the blue small circle is here at this particular point, whereas the center of the sphere or the Earth is at point C here. Now, all the parallels of latitude except the equator are small circles. Whether it is 10 degrees, 20, 30, 40, 50, north or south, all these parallels on the surface of Earth represent small circles because their plane does not pass from the center of Earth, and their radius is not equal to the radius of the Earth, and the center of these circles is not the same as the center of the Earth. So that was the concept of a great circle and a small circle.
Sir, as it was said, only one great circle can pass through 2 points on the sphere. And if those 2 points are on the same hemisphere, like in the northern hemisphere or the southern hemisphere, still the great circle can pass through it?
Yes, beta, why not? To give you an example, let us say you have a point on the Greenwich meridian at 60 degree north, and you have another point on the Greenwich meridian at 30 degree north. Right, both are in the northern hemisphere. Now there is a great circle which will pass through them, and that would be the meridian itself.
And sir, if okay, sir, okay, understood.
Okay, or any other doubt, beta? Okay, let's move ahead then. We move on to spherical triangle.
Now we move on to the concept of a spherical triangle. We are familiar with plane triangles. We use them very often in our calculations. Now we are going to understand what is a spherical triangle. We have the diagram on the screen. A spherical triangle is a triangle on the surface of a sphere formed by the intersection of three great circles. Now, as you can see in this particular diagram, we have a triangle being formed on the surface of a sphere. This is a 3D diagram, and you can see this triangle being formed A, B, C. Now, this triangle is being formed on the surface of a sphere. That's number one requirement for a spherical triangle. And second, all the three sides of this triangle, you can see side AB, it is an arc of a great circle. The second side BC is also an arc of a great circle. And the third side AC is also an arc of a great circles. All the three sides of the triangle should be the arcs of great circles. So that's a mandatory condition to be fulfilled for a spherical triangle. If any one of the sides is not the part of a great circle, or you can say if any one of the sides is the part or arc of a small circle, in that case, the triangle is not a spherical triangle. For a triangle to be called a spherical triangle, it is mandatory that all the three sides should be the arcs of great circles only. Now, in a triangle, there are total 6 components. There are 3 angles and 3 sides. In plane geometry, the angles are measured in degrees, whereas the sides are measured in units of length, that is meters, centimeters, millimeters, etc. But in spherical triangle, there is a difference, a significant difference. All these 6 parts, that is the 3 angles of the spherical triangle, like in this case, angle A, B, and C, as well as the 3 sides of the spherical triangle. You can see these 3 sides, AB, it is also represented as small c. Then BC, it can also be represented as small a. And the third side, AC, which can also be represented as small b. The side is either represented by the vertices which connect to form that side. Like for this particular side, we can call it as AC, or you can also call it the small letter of the angle opposite to it. Now the angle opposite to this side is angle B. So you can also represent this side with small letter b. So in a spherical triangle, all these 6 parts, that is the 3 angles as well as the 3 sides, are measured in units of angles only. We do not measure the sides of the spherical triangle in units of length. They are all measured as angles. Now a doubt can arise in your mind that it is understood that angles are measured in angular units. So we can measure angle A, B, and C in the angular units of degrees and minutes. But how do we measure the side of a spherical triangle in degrees and minutes? Now to understand that, for easy understanding, the magnitude of the side of a spherical triangle is basically the angle subtended by it at the center of the sphere. So let's take, for example, side AB. You can see this is side AB. Now if I join A with the center of the sphere here, and I join B with the center of the sphere. Now both these lines joining A and B with the center of the sphere make a angle at the center. Now this angle is basically the measurement of this particular side of the spherical triangle. So repeating again, the magnitude of the side of a spherical triangle is the angle subtended by it at the center of the sphere. Okay, having understood the concept of a great circle, a small circle, and a spherical triangle, now let's go into our first very important formula used in spherical trigonometry, that is the cosine formula. Now this formula is not only used for great circle shading, but also used at many places in celestial navigation as well. So this is very important for the full navigation part. Now for this, let me make a rough diagram for a spherical triangle. You can see one side of the spherical triangle. Now we know all the sides of the spherical triangle are arcs of the great circle. So let me mark it as a GC. You can see the second side of the spherical triangle now in green color. This is also the arc of a great circle. Let's mark the third one now. You can see the third side of the spherical triangle, which is again an arc of a great circle. Let's give it a name also. Let's mark one of the vertices as P. Let's mark the second vertex as A and the third one as B. So Papa Alpha Bravo PAB triangle is a spherical triangle. That means it is made on the surface of a sphere, and all three sides of this triangle are arcs of great circles. Now the cosine formula says cos of any angle of a spherical triangle is equal to cos of opposite side minus cos of adjacent side 1 multiplied by cos of adjacent side 2 whole divided by sine of adjacent side 1 multiplied by sine of adjacent side 2. Now, what do we mean by the opposite side and the adjacent side? Let's try to understand. Let us consider any one angle of this triangle. Let's consider angle P. Now, you will see there are two sides of this triangle which are making this particular angle. In this case, angle P is being made by the side Papa Alpha, PA, and Papa Bravo, PB. Now these two sides which make this particular angle are known as adjacent sides. The third side, which is not in any way involved in making this angle, in our case this is side AB, Alpha Bravo. This side is known as the opposite side. So this is how we explain the adjacent sides and the opposite sides. You can see that in this formula, the cosine formula, on the left hand side we can have any angle. In our case, angle Papa, angle Alpha, or angle Bravo. And on the right hand side you see all the terms are related to the sides of the triangle. So you have opposite side, then adjacent side, again adjacent side and adjacent side in the denominator. So it tells us that if we have all the three sides of this triangle available to us, we can calculate any of the angles of this spherical triangle. Now let's try to understand the application of the formula for a particular angle. Let's consider angle P only. So we will try to apply this formula considering angle P. So the formula says cos of any angle. In our case, it will be angle P now. You can see this angle P marked here in the diagram. So the cosine formula, once applied to angle P, will give us cos of angle P is equal to cos of AB. You can see AB is the opposite side to this angle P, minus cos of PA. You can see PA is the first adjacent side, multiplied by cos of PB. You can see PB, Papa Bravo, is the second adjacent side to this particular angle, whole divided by sine of PA, that is adjacent side 1, multiplied by sine of PB, that is adjacent side 2. So cos of any angle is equal to cos of opposite side minus cos of adjacent side 1 multiplied by cos of adjacent side 2, whole divided by sine of adjacent side 1 multiplied by sine of adjacent side 2. So that is the application of the cosine formula. We can apply this to any of the angles as required by us, as we have done for angle P. Now let's try to go a little deeper into the formula and try to understand what are the situations, scenarios, or questions in which this cosine formula can be used. There are specific conditions in which we can use the cosine formula. We have the spherical triangle rough diagram here, same Papa Alpha Bravo triangle. Now this cosine formula can be used in two conditions or two scenarios. What are these two conditions? Number one is when all the three sides of this spherical triangle are known to us. Papa Alpha, Papa Bravo, and Alpha Bravo, all three sides are known to us. Then we can apply this cosine formula and we can calculate all the remaining angles of this triangle. Angle Papa, angle Alpha, angle Bravo, all three can be easily calculated. We just saw in the formula itself, on the right hand side, we have all the sides. So having all the sides known to us, any of the angles can be found out. Now the second condition or scenario in which cosine formula can be applied is when we know any two sides of the spherical triangle and, very, very important, included angle known to us. What do we mean by the included angle? If any two sides of this triangle are known to us, let us say we know Papa Alpha, the green color side of the triangle. We know Papa Bravo, that is the blue color side of the triangle, and the included angle. The included angle between these two sides is the angle P, angle Papa. So in this case also, two sides known to us and the included angle known to us, cosine formula can be applied. Now when we apply the cosine formula, the first thing which we will be able to calculate or find out in this triangle is the missing side, the unknown side. In this case, the side AB, Alpha Bravo. Now, once the missing side has been known, has been calculated, then we again have access to all the three sides of the triangle, and the remaining two angles, that is angle alpha and angle bravo, can also be calculated and found out. Now, important thing to understand here is that the angle which you know should always be the included angle. If you know an angle other than the included angle, then in that case cosine formula will not be applicable. So to give you an example, if you know side PA, the green color side, and side PB, the blue color side, and you know angle A. So in this case, angle A is not the included angle, and we will not be able to use the cosine formula here. Again, if angle B is known, same thing happens. Angle B is not the included angle, and we will not be able to use the cosine formula here. So it is very important that we know the two sides, any two sides of the triangle, and the included angle for the cosine formula application. Now, a doubt may arise in your mind that in case we have two sides and a angle which is not the included angle, how to proceed ahead and solve that triangle. So in that case, we can use, or we have different methods with which it can be solved, but they are not required right now as far as the great circle problem is concerned. So we will see what is to be done when we come to those questions. For now, we will always have one of these two scenarios. Number one, when all the three sides are known to us, and number two, when any two sides and the included angle is known to us.
Beta, before we proceed ahead to Napier's rule, any doubt in your mind till now?
No, sir.
Okay, great. So cosine formula is done. Then let's proceed to the Napier's rule, second important relationship which we use for spherical trigonometry.
Let's now go into the second important formula in spherical trigonometry. This formula is also used to solve spherical triangles, and this is known as Napier's rules. Now, these Napier's rules are applicable to special spherical triangle. What is the speciality in the spherical triangle? The speciality could be either a 90-degree side or a 90-degree angle. As you see in the diagram, we have a triangle PAB, and in this triangle, the red side, the side AB, is a 90-degree side. Now we are aware that in a spherical triangle, the angles as well as the sides are measured in angular units. So if any one of the sides of a spherical triangle is 90 degrees, then it is known as a quadrantal triangle, and Napier's rule can be applied to it. A 90-degree side is represented by making a rectangle in this particular way. So whenever you see a diagram of a spherical triangle with any one of the sides having this rectangle, it tells you that this is a quadrantal spherical triangle or a spherical triangle whose side is 90 degrees. The second speciality could be a 90-degree angle. So again, we have a spherical triangle PAB at the bottom part of the slide. And you can see that in this spherical triangle, the angle B which we have is a right angle. So if any spherical triangle has this speciality of 90 degrees, either it has a 90-degree side or it has a 90-degree angle, then we can apply the Napier's rule to that particular triangle. Let's now see the application of the Napier's rule. First, we will see the application of Napier's rule in a spherical triangle having a right angle or having a 90-degree angle. Now we have the PAB triangle on the screen, and we can see that angle B of this triangle is a 90-degree angle. Now to apply the Napier's rule, we first make a circular diagram, and this circular diagram is known as a cartwheel. So first of all, to make that diagram, we draw a circle. You can see the circle on the screen now. And we make a cross in that circle in this particular way. You see one line and the second line. Now from the center of the circle, we draw a vertically upward line. So with this, you see the circle is divided into 5 parts. So there are total 5 parts in this circle. Now what we do is, in the bottom 3 parts, the bottom 3 parts of the cartwheel, we write down 90 degrees minus, 90 degrees minus, 90 degree minus. So in the bottom 3 parts, which are the bigger parts, we write down these values of 90 degree minus. Now we identify the right angle in the PAB triangle. In this particular example, we have angle B as our right angle, and this 90-degree angle is written on top of our cartwheel. So we have the angle B marked at the top of the cartwheel now. After this, what we do is, from the 90-degree part, in this case angle B, we start to move clockwise in our triangle. So our triangle, the PAB triangle, has total 6 parts. There are 3 sides and 3 angles of this triangle. So from the right angle, which is angle B in this case, we move clockwise in the triangle. Now when we move clockwise, you can see the clockwise direction being shown by the laser pointer. When we move clockwise, the next part of the triangle which comes after angle B is the side AB, the red color side. So what we do now is, we start to move clockwise in the circular diagram in the cartwheel also, and we fill up these parts in the different sectors or different segments of the cartwheel. So from the B part in our cartwheel, we move clockwise, and the next part which we have, we fill up the part of the triangle which is side AP. So going clockwise from B, the first part which comes as AB, going clockwise from B in the cartwheel, the first part is filled up as AB. Now after AB, the next part in the triangle which comes is angle A. Angle A is the next part. Now when we go to the cartwheel clockwise after AB, in this next part we have to fill up angle A. So we have already written 90 minus 90 degree minus 90 degree. Now from the right angle cartwheel, we have already written 90 degrees minus, and here we fill up the part PA. Coming back to the triangle, after side PA, we have angle P in the triangle. And moving further clockwise in our cartwheel in the next part, we have 90° minus already written, and we fill up this angle P after 90 minus. So this part becomes 90 degrees minus P. Moving further clockwise, we have side PB of the spherical triangle, the blue color side. And moving further clockwise in the cartwheel, we have this part which is remaining now, and we fill up the side PB in this particular part. Going back to the triangle, after side PB, we reach back to the right angle B, angle Bravo, and you will see that in the cartwheel also, once we fill up these parts, we reach back to angle B. This is how the cartwheel is filled up. So from the right angle, we start to move clockwise. First part is AB, next part is angle A, next part is side PA, then angle P, and in the end PB. We fill up all these parts in the cartwheel going clockwise. So you go clockwise from B, the first part which comes as AB is filled up here. The next part which comes as angle A is filled up here in the second part. The next part which comes is side PA, filled up in the third part of the cartwheel. Next part which comes is angle P, and the next one PB, coming back to Bravo. So this is how the cartwheel is filled up. Now, once the cartwheel is filled up, we can apply the Napier's formula now. What is this Napier formula? Let's see. There are two formula in the Napier's rule, which are used in the Napier's rule. The first one is sine of the middle part is equal to tangent of adjacent part 1 multiplied by tangent of adjacent part 2. This is the first formula to be used. And the second formula is sine of the middle part is equal to cos of opposite part 1 multiplied by cos of opposite part 2. Now, these are very, very important formula, and it should be memorized well. Now, when we look at these formula, they have used the terms middle part, adjacent part, and opposite part. So a doubt arises in our mind, what is this middle part, what is the adjacent part, and what is the opposite part? We will see the application of the Napier's rule now in the coming slides. And then these middle, adjacent, and opposite parts fundamental will become clear in your mind. Now, the basic philosophy in the Napier's rule application is that if you have a special spherical triangle, means one of the parts is 90 degrees, either an angle or a side, Napier rule allows us to calculate any part of that particular triangle if we know any two parts of the spherical triangle other than the 90-degree part. I will repeat once again. In a special spherical triangle, if you know any two parts, it could be two sides, it could be two angles, it could be one side and one angle. If you know any two parts in a right-angled triangle, you can find out any of the remaining parts using the Napier's rules. So this is the basic philosophy or concept behind the Napier's rule. Now let's see the application of Napier's rule. Now a very easy way of remembering the Napier formula is, you see on the left hand side of both these formula, we have sine of the middle part. So left hand side, sine of the middle part is quite easy to remember. Now on the right side, you see we have tangent adjacent part 1 multiplied by tangent adjacent part 2. Or in the second case, we have cos opposite part 1 multiplied by cos opposite part 2. To remember it easily, to memorize it easily, you remember that tangent and adjacent, they are rhyming words. They both have the same tone. Tangent and adjacent, they always go together. And cos and opposite, they both have the sound of O. Cos and opposite, they always go together. If you remember it this way, you are never going to forget it. Tangent and adjacent, they go together. Cos and opposite, they go together. So depending upon which formula you are using, depending upon which parts are available to you, if adjacent parts are available, you know I have to use the tangent formula. If opposite parts are available, you know I have to use the cos formula. A very, very easy way to remember it. Another important thing to understand is that we have filled up the parts going clockwise in the triangle PAB. We have moved clockwise in the cartwheel also. Now, just to make you aware that if instead of clockwise, somebody wishes to go anti-clockwise, or by mistake, let us say you move anti-clockwise. Even if you move anti-clockwise, the application of the Napier's rule will still be accurate. If you move anti-clockwise in the triangle and you move anti-clockwise in the cartwheel, even then the application of Napier's rule will not go wrong. It will still be correct and accurate. Now, in case somebody moves anti-clockwise in the triangle and he moves clockwise in the cartwheel, even then the application of Napier's rule will be accurate and correct. So to put it in short, the Napier's rule is quite robust, and a little bit of change in the application is not going to make any difference in your answer. As I told you that Napier rule says if we know any two parts of the spherical triangle other than the 90-degree part, using Napier's rule, we can find any other part of the triangle. So important thing to remember is that we should know two parts of the spherical triangle and they should be other than the 90-degree part. So leaving the 90-degree part aside, if you know any of the two parts, like in this particular triangle, one part is side AB, then you have angle A, then you have side PA, angle P, and you have side PB. So 5 parts which are there in this triangle. Out of these 5, if you know any two parts, it could be two sides, it could be two angles, it could be one angle and one side, you can find out all other missing parts using the Napier's rule. So this is the same PAB triangle which we had in the previous slide, and the same cartwheel is filled up at the bottom part. So exactly same. Now, let us assume that in this particular triangle, triangle PAB, we know two parts. Let's assume that we know side PA, Papa Alpha side. I have shown a tick mark here representing that this part is known to us. And we also know angle P. So again, you see a tick mark coming at angle P. These are the two parts of the spherical triangle PAB which are known to us. And now using Napier's rule, we want to find out angle A. We can find out anything else. See, there are 3 unknown parts now. One is angle A, another is side AB, and the third unknown part is side PB. We can find any of the parts, unknown parts, using the Napier's rule. But let's assume that we first of all want to find angle A. So let's show a question mark at angle A. This is the angle which we need to find out. Now we first need to identify these parts in the circular diagram or in the cart wheel. So the unknown part as well as the known parts, we need to identify them. Now the parts which are known to us are side PA, side Papa Alpha is known to us. Let's identify this in the cart wheel. Papa Alpha part is in this segment of the cart wheel. So let's put a tick mark here indicating that this part of the cart wheel, this sector of the cart wheel is known to us. The second part which is known to us is angle P, and in the cart wheel angle P is in this particular segment. So this segment of the cart wheel is also known to us. So let's put a tick mark here also. You see the two parts which are known to us identified by tick marks in the cart wheel. Now let's identify the part which we are finding out. In this case, we are trying to find out angle A. So angle A is in this particular segment of the cart wheel. So let's put a question mark here indicating that this part needs to be found out. Now once you mark out these three parts in the cart wheel, we need to identify, out of these three, we need to identify a middle part. Now, how do we identify a middle part? The middle part should be identified in such a way that the remaining two parts, both of them, should either be adjacent to the middle part or both of them should be opposite to the middle part. Now, what do we mean by adjacent and opposite? Now, to give you an example, let's consider the part 90 degree minus PA. So let's consider this particular part of the cart wheel. Now you are able to see that there are two parts of the cart wheel which are adjoining or adjacent to this particular part. We picked up this part of the cart wheel as an example, 90 minus PA. Now there are two parts of the cart wheel which are sharing a side, or they are adjoining, or they are adjacent to 90 minus PA. Which are these parts? One part which is sharing its side with 90 minus PA is this one, 90 minus P. They are sharing this particular side. And other part which is sharing a side with 90 minus PA is this one, 90 minus A. It is also sharing this particular side. Now these parts which are adjacent to the part which we assumed in the first place are known as adjacent parts. Since they are adjacent to the part which we selected in the beginning as middle part, they are called as adjacent parts. Now you see there are two more parts of the cart wheel. One is this part, part PB. PB does not share any side with 90 minus PA. So the part which does not share anything or which is not adjoining to the middle part is known as a opposite part. So for 90 minus PA, PB is a opposite part. Similarly, the part AB is again opposite part to 90 minus PA. So again repeating, first of all, you need to consider one part of the cart wheel as the middle part. Out of these three, the known and unknown parts, one part has to be considered as the middle part. Now, what is the criteria for making a middle part? The other two parts should either be adjacent to it or the other two parts should both be opposite to it. The middle part should not be selected in such a way that one part becomes adjacent and the other part becomes opposite to it. So let me explain it to you now. We have identified these three parts in the cartwheel. Out of these three parts, two parts are known to us, which are shown by a tick mark, and one part is what we want to find out, which is shown by a question mark. Now, we want to pick up a middle part out of these three. Let's say somebody picks up the 90 minus p as a middle part. Now, if you pick 90 minus p as a middle part, the part 90 minus pa becomes adjacent to it, and the part 90 minus a becomes opposite to it. Now, this does not suit our criteria. Our criteria is the remaining two parts should either both be opposite to it or both of them should be adjacent to it. If I pick up 90 minus p as my middle part, 90 minus pa becomes adjacent and 90 minus a becomes opposite. So 90 minus p cannot be picked up as middle part. Now let's try with 90 minus a. If I pick 90 minus a as my middle part, 90 minus pa is adjacent to it and 90 minus p is opposite to it. So again, our criteria is not fulfilled, not satisfied here. We want to pick up the middle part in such a way that the remaining two should both be either opposite to it or they should both be adjacent to it. Let's now try out with the 90 minus pa part. If I make 90 minus pa as my middle part, you will see that 90 minus p is adjacent to it and 90 minus a is also adjacent to it. So this satisfies my criteria. If I pick 90 minus pa as my middle part, both the remaining parts are adjacent to it. Now, why do we want to have both the parts as adjacent parts or both the parts as opposite parts? The reason is, if you look at the formula, our formula, the two formula which we have, either consists of adjacent part 1 and adjacent part 2, or it consists of opposite part 1 and opposite part 2. We do not have a formula in which we have adjacent part and opposite part together. So that's why we are picking up a middle part in such a way that the remaining two are either both opposite to it or the remaining two are both adjacent to it. Then the formula can be easily applied. So once you have identified the middle part, and in this case we have two adjacent parts, we can now apply the formula. The formula which we are applying here is sine of the middle part is equal to tangent adjacent part 1 multiplied by tangent adjacent part 2. So you see the middle part is 90 minus PA. So you have sine of the middle part as sine of 90 minus PA. Tangent adjacent part 1. One of the adjacent part is 90 minus P. So you see tangent 90 minus P into tangent adjacent part 2. The second adjacent part is 90 minus A. So we have tangent 90 minus A. Now, if you have a look in this applied formula, we know the PA side of this triangle. It is known to us. You have a green tick mark here indicating that it is known. We assume that this is a known part. So I have marked this in green here. Then coming to the right hand side, the angle P is also known to us. We have a tick mark. We assume that angle P is known to us. So I have marked this tangent 90 minus P also in green. These are the two parts which are known to us. Now the only unknown in this equation is 90 minus A. So angle A is what we were trying to find out. So tangent 90 minus A is the only unknown part. Now once we put the values of the known parts, that is BA and P, in this formula, we will be able to easily get the value of angle A using the scientific calculator. So this is the application of the Napier's formula.
सर एग्जाम में आता है सर ये वाला मतलब 90 माइनस ये नेपियर्स रूल?
Yes, beta, many of the questions which we will do now, they will have this Napier rule application. So we will be solving questions based on this. Okay. So this was Napier rule application for 90-degree angle. Now let me quickly revise to you the application for 90-degree side. The only difference in Napier rule application for 90-degree side is that when we fill up the cartwheel, in the bottommost part, we take this 90-degree to the end. We don't write 90 minus, but we write minus 90 instead. So the part of the triangle comes in the beginning and the 90 goes to the end. This is the only difference when you apply the Napier's rule for a 90-degree side spherical triangle. Otherwise, the application is exactly the same. The formulas are exactly the same. So this completes our application and understanding of Napier's rule, cosine formula, and spherical trigonometry. So any doubts from your side, beta?
So what was the last point? 90 minus the side. What do you mean by that?
Okay, let me go back. Now you look here, beta, this is application for 90-degree angle. You see in the bottommost part, concentrate your attention to the bottommost part. In the bottommost part, we had 90-degree minus and then either a side or a angle of the triangle. In this case, it was PA. Correct?
Yes, sir.
Now, when you go to 90-degree side, this part of the triangle comes in the beginning and 90 goes to the end. Their positions are interchanged. Did you understand it, beta?
Negative, sir.
Okay. Okay. बेटा ये जो बॉटम वाला पार्ट है इसमें हमने ये जो 90 माइनस लिखा है इसका ट्रायंगल से तो कुछ लेना देना नहीं है. इट इज नॉट एनी पार्ट ऑफ द ट्रायंगल. करेक्ट?
यस सर.
हमने ये 90 माइनस तीनों वाले बॉटम पार्ट में फिलअप किया और फिर ट्रायंगल्स के पार्ट को क्लॉकवाइज मूव करते हुए फिलअप कर दिया. राइट?
यस सर.
ओके. नाउ फॉरगेट अबाउट 90 डिग्री एंगल. लेट्स गो टू 90 डिग्री साइड. नाउ अगर मैं सेम चीज़ इस 90 डिग्री साइड में भी करता तो मैं लिखता 90 माइनस, यहाँ भी मैं लिखता 90 माइनस और जो ट्रायंगल के पार्ट्स हैं उनको फिलअप कर देता. सो दिस बॉटम पार्ट वुड बी 90 माइनस पी.
यस सर.
But you see it has been turned now. 90 has gone to the end and p has come in the beginning. It has become p minus 90.
Got it, sir.
This is the only difference. So is it okay, beta? Is it clear now?
Yes, sir.
Okay. All right. So this completes our spherical trigonometry.